So Chapter 7, Transmission Media. This is actually one of those important chapters. Here we talk about guided and unguided transmission, essentially wired versus wireless. We talked about the definitions and the forms of energy, background radiation, noise. Then we start getting more in depth between the different types of communication wiring or transmission types. So 7.5, we start getting into our guided, more specifically our copper-based portion. Then 7.8, we get into our guided fiber optic or optics. Then after that, we get into our lasers and our IR or our infrared. Then in 7.13, we get into our wireless or unguided transmission. Within that, we have to talk about our satellites, and that's our GEOs, our LEOs, our medium-range satellites. And then about 7.19, we start talking about trade-offs among the different types of transmission medias, trying to figure out which one's best. Then we kind of end with noise and channel capacity. So this chapter again continues our discussion within data communication. Now we're actually talking about the wiring. How is our signal going from one location to another? Again, that's going to be our wired, wireless, guided, unguided. We're going to lead into explaining how shielding and forms of cable or forms of transmission media can prevent noise. And again, we're going to end with the concept of capacity. So, first thing is, why or how can we divide our medias into different classes or categories? Two ways: the type of path or the form of energy, or a combination or a hybrid of both of them. So this is actually how we get to our guided versus unguided. That would be our wired versus wireless. And then even under there, within our wire, we can actually classify them even more. Copper versus optics. Underneath wireless, radio waves or radio frequencies versus satellite or versus laser or versus, well, laser's optical, sorry about that. Radio waves versus Bluetooth versus WiMAX versus satellite. I mean, there's other categories underneath wireless. It's not just wireless and wired. There's subcategories underneath both of them. We're actually going to end with our satellites and our orbits, terrestrial versus non-terrestrial. So I'm going to hold off on certain parts of this because that's at the very end. So here is a very basic breakdown of our types of communications or transmission medias. Here we're breaking them down from energy types: electrical, light, electromagnetic. Underneath electrical, twisted pair, coax. You'll notice those are copper-based. Underneath our light, that would be our optics, our fiber optic, our infrared, our laser. Lastly, electromagnetic. That's going to be our radio or wireless. And that's going to either be classified as terrestrial radio, radio on the ground, or our satellite, non-terrestrial. I mean, even with these, we can break them down even further. Terrestrial radio, radio frequency, or Bluetooth. I mean, this is going to show you that we can break it down. It all depends on what's going to be the easiest way to do the breakdown. So when we start talking about copper specifically, we're going to talk about the flowing of electrical current and how it flows to complete a circuit. Essentially, there's going to be two wires or two portions of a wire. One sending the impulse and one receiving it. So that actually gets to complete a circuit. Same thing in a typical house lamp. One actually sends the electrons, and one actually the electrons flow back. Now, how these are actually protected is they're wrapped in a plastic coating to help insulate the electronic components of the wire. That way the wires themselves don't touch, and nothing else gets on the wire to impede the signal or anything like that. So when we talk about computer networking cable or computer networking medias, we have to do what's called an alternate form of wiring. But before we can talk about that, we have to just understand a few other things. We have to understand that electrical cable actually radiate noise, and then actually goes out into the environment. That means if there's too many electrical cables close together, they're all radiating noise, and that noise can be picked up from other cables. When another cable gets the radiation, it can induce a small signal. Basically, the possibility of having too many cables close together and having one just create a whole new signal, it's possible. Not super plausible, but it is possible. And I have seen it happen, so we have to be careful of that. There are certain types of shield that can actually absorb the radiation, thus acting as a shield. So when you start talking about different types of copper-based media, we talk about three major types: UTP, coax, and STP. UTP being unshielded twisted pair. That's what most people are commonly see or commonly deal with. Next, coax. That's if you have broadband or you have cable, you're pretty familiar with coax. And then last is shielded twisted pair. So the main differences between UTP and STP is UTP has no shield. STP does. So now that we have that basic understanding, we can actually look at why they're twisted. If the wires are not twisted, you'll actually see a source of radiation. There's going to be a difference in the cables. Versus figure B, if they're twisted, there is no difference. If we match up the blue cable on the bottom, for example, +3, +5, +3, +5, and then we add up the gray, +5, +3, +5, +3, there is no difference, which means they are less susceptible to noise. Essentially, without the twists, when the wires are in parallel, there's a higher probability that the closer the wires are together, the more likely there's going to be noise from other wires' radiation. While granted, the twisting pair does allow for some immunity of background radiation, it doesn't fix all of them, it's just some of them. If the intensity of the noise is too high, or if the cable is too close to other sources of noise, the twisting may not be enough. That is actually why we have our shielded twisted pair. Just in case that the typical twist is not good enough, we have an additional step that we can do. What we could also do is use coax. One of the nice things about coax is it might not be as great as shielded twisted pair, but actually it has additional layers of protection. We have a center core, a copper core. Then we have some form of plastic coating or insulation or cladding. Then we have a metal mesh shield. Then we actually have an outer protective layer for protecting the entire cable as a whole. that shield actually removes or mitigates a lot of the noise that this cable gets. The nice thing with the coax is you can actually put it in any type of environment and it would be okay. It's using that braided wire instead of a solid metal shield helps allow the cable to keep staying flexible. So again, one of the popular variations is shielded twisted pair. The shielding can either be a braided mesh or a solid metal shield like tinfoil. But again, depending on our requirements, one may actually end up being less flexible. So, who makes these cable standards? I mean, we've been talking about UTP and STP and coax, but I mean, who actually makes our standards for our cable? So there's big three ones that we have to learn. ANSI, which is the American National Institution, or American National Standards Institution, sorry. The Telecommunication Industry Association, TIA, or the Electronic Industry Alliance, EIA. So the last two you might see as EIA-TIA or TIA-EIA. Doesn't really matter which one is first. But they actually jointly together develop a lot of telecommunication and electronic industry standards. For example, our category cable, our Ethernet cable heads, the way that the pattern is laid out is it's an EIA-TIA standard. So I mean, are there different types of standards for our category cable? Here's a common 7, well 8 technically. Don't pay too much attention to the data rates because these data rates are way off. Cat5e should be able to handle 1000 megabits per second versus Cat6, that's 10,000 megabits per second. So, I mean, these numbers are slightly off. But the lower or the higher the number, the lower in the chart that we go, Cat5e, Cat6, Cat7, those are actually our newer cable standards. Those are what we typically deal with. In industry, normally we're looking at Cat5e, Cat6, or Cat6e. Those are our big ones. So let's transition away from our copper into our fiber optic, or our optics, sorry. So if we deal with our optics, what three are we dealing with? We're going to deal with fiber optic itself, infrared, and point-to-point lasers. So all of these have one very big common thing together. And that actually is that on one side of the cable, we have something generating light, and on the other end of the cable, we have something that's light sensitive. These cables allow for one-way communication, so we have to have two cables to allow for two-way communication. Just like within our circuits, we had to have one for sending and one for receiving. Same thing here. So the next question then becomes, can light travel around a bend in the fiber? And so the interesting thing here is we're looking for a critical angle. And essentially, if light hits one of the sides of the fiber at the wrong angle, then we have a problem. For example, we can actually have light reflect, so that would be section C, and then it would actually bounce down the cable correctly. We could actually have the critical angle the wrong angle and have it actually be absorbed into the side. That'd be B. Lastly would be refraction. The critical angle actually is not correct and thus leads to the light being refracted, thus leading to the light not going all the way down the cable. So reflection is the optical fiber the reflection is not perfect. The zigzag going down the media actually cannot go on indefinitely. However, it has been shown that the zigzag actually forces the proton to go a little further than if the proton was just shot down the center of the cable. The further the light goes, the more dispersion there might be. And after a critical point in time, the dispersion gets so problematic, you don't know if it was the data that was being sent was truly what was originally sent. Here's an example. Sent versus received. Received, just the degradation is so bad that you're not sure if that was a 1, like it was an actual signal, or if there was just noise and then amplified. This is a huge error that noise can cause. When we deal with our fiber optic, we have two major types, multi-mode and single mode. Multi-mode is less expensive and is typically used when performance is not important, meaning it's the slower of the two, but it's cheaper. Single mode is the most expensive and provides the least dispersion. However, it has the smallest diameter and it can go a lot farther, but it is incredibly expensive as opposed to multi-mode. So again, the light being sent and received is typically some form of either LED or injected laser diode, some form of diode, and on the receiving end, some form of photosensitive or photo diode, something that's going to recognize that it's getting light. So let's look at some of the pros for fiber. It's immune to electrical noise because it's light, it's not copper based, so the electrical noise is not an issue. It can have higher bandwidth. That's very subjective because there's a lot of new articles out talking about higher performance copper. So generally though, fiber, it can go further and can have more bandwidth, though one of the biggest issues is cost. So again, optical is immune to electrical noise, less degradation, typically higher bandwidth, though costs. Copper, it's cheaper typically. It's normally requires a lot less expertise and is a lot less broken. Fiber optic you can easily break, and that's kind of subjective. I've worked with fiber for a while, and fiber is, I mean, pretty durable. I mean, not super durable, but not like super rigid either. Though, when we talk about this, when we start talking about cost, you also have to think about the environment that you're putting it in. Is there going to be noise? Is there not going to be noise? Is it going to be upgraded in a few years? So there's a lot of things to consider when we start talking about the type of transmission media that we're going to be using. Next would be our infrared. This is going to be some form of point-to-point higher frequency laser, and it's typically used for TV remotes. It actually is required to be point-to-point. However, it can reflect off of ceilings or walls. Typical speeds, I'll let you read through them. So essentially, the point-to-point laser communication is a pair of devices that allow you to, through a line of sight, share small bits of data. If you think about like the Samsung Galaxy 3, 4, 5, If you're in close enough proximity, the touch option that allows you to actually touch your screen and you beam or transfer a photo from one piece or one device to the other device, same thing. Or if you have an Apple device, AirDrop would be something similar to that. Laser communication really works well if distance is an issue and you have proper line of sight. For example, two buildings that are far away, if there's nothing in between them, you can actually beam data in between them instead of having to worry about some form of wire between both. Lastly, and the most common form of our media types are unguided or are wireless. With this, we start talking about predominantly radio frequency because that is our most common form of unguided transmission. And actually, most can argue that this is actually our most popular form of transmission media now. It's just Wi-Fi has been on the rise for the last 5-6 years, and now with mobile devices being as strong as they are, Wi-Fi is pretty much taking over. Not in all areas, but for typical home users or mobile users, Wi-Fi definitely. So the benefits of Wi-Fi is it can penetrate objects. It can go through walls. However, it does use a specific form of the spectrum, which means it can be susceptible to other forms of noise. I do apologize if you can hear all the background noise. There's a pretty heavy thunderstorm outside right now, so that's been fun times. So the next question then becomes, who allocates the frequencies used for our radio frequency? The FCC, or Federal Communication Commission, controls our frequencies. So let's talk about a little bit more about our RF frequencies. And that's normally the frequencies between 3 kilohertz and 300 gigahertz. For most of the time, though, it's better to see it represented as a chart. So our 1 gigahertz typical range is our radio and TV. For example, the 102.7, that would be in megahertz. That's a fairly popular, well, at least in the West Coast, that's a country station, pretty much no matter where you go. But above that would be our microwave, then our infrared, then our visible light, then our ultraviolet light, then X-rays, and our gamma rays. But again, we're dealing with mainly 3 kilohertz to 300 gigahertz. That's our radio and TV. This is always a good chart to kind of go slow on just because this is a really big thing. We actually are only able to see such a small portion of the light spectrum, or the electromagnetic spectrum, that we miss so much because we don't actually see it. Even just our radio and TV, that's such a small portion of it. Okay, moving on. Signal propagation. So when we start talking about propagation, we have to think about how is the signal going to reach the endpoint. When you start broadcasting, as it goes further and further and further away from the tower, the waveform starts getting slower and slower and slower. Essentially, as you get further from the tower, the lower the signal strength. The signal strength will still be there a few miles away, just sometimes it's so low that we don't get to see it. Well, we don't normally get to see it anyway, but our devices don't detect it. But the signal is still there. Now we have to talk about two very big things. Terrain. Terrain is the Earth's surface. Our terrain can actually affect our wireless. It affects our wireless predominantly in the form of absorption. If our wireless gets absorbed into the Earth, it kind of gets blocked. For example, I live in Las Vegas. Las Vegas is in a valley, so we have large mountain ranges surrounding us. If we try broadcasting outside of the valley, the mountains actually absorb our radio frequencies. So we actually had to put antennas on top of the mountains so that we could actually send out signals. Now let's start going into our terrestrial versus non-terrestrial. Terrestrial, on Earth. Non-terrestrial, not on Earth. That's about it. So let's talk about low range, medium range, and higher range. So depending on the range, we actually have the ability to get faster speeds. Higher frequencies mean better speeds. So that's true with almost all Wi-Fi. Now, since we talked about our Wi-Fi, we have to talk about one more form of wireless or unguided transmission. That's our satellites. So our satellites orbit the Earth. Now, the orbit can happen in very specific time periods. We can actually have a low Earth orbit, a medium Earth orbit, or a geostationary Earth orbit. Low Earth orbit means it actually can transverse the planet quicker. A medium orbit means it will actually transverse the planet a little bit slower. A geostationary means it will actually stay right above a specific point, period. Our most common one is going to be geostationary. If you think about our satellite companies, Dish Network, for example, they actually have to have a satellite above a specific area regularly. Versus, I don't want to say spy satellite, but spy satellite or other form of telecommunication satellite that might circle the globe. Because they're going to look at different portions of the globe in different areas, where a geostationary one doesn't. It just wants to stay above a very specific geographic spot all the time. For our geostationary, normally they are at our equator and they stay stationary. Basically, they rotate at the same speed that the Earth rotates, so it seems as if they are there. Here's a great example of how we have both ground and satellite, and how that satellite actually allows for non-point-to-point. So our receiving and our sending ground stations, they cannot talk to one another directly because of the curve of the Earth, but they can talk to the satellite, and then the satellite acts as an intermediary in between the two. Here is the math formula for the speed at which a satellite has to stay going so that it can be part of a geostationary orbit. I've never ever had to use this. Some people might find it interesting, some people might not. It's there just in case you want to look at it. So, how many satellites must we have to cover the Earth's surface? The typical number is 3. Though, that's a lot of information to pass just between 3. So, minimum is 3. That doesn't mean that 3 is the best number, it just means minimum you need 3. Low Earth orbit we already talked about. That is a shorter delay, it travels faster. Though The issue with here is because it does go faster, it can lead to faster communication or spottier communication. It kind of all depends on how you look at this. Oh, helps if I go forward, not backwards. So, moving on. We only have 2 more slides left, and this is one of, I think, the most important one. So, what type of media are you going to choose? And normally it depends on cost, data rate delay, effects on signal, the environment, the security, your budget. Honestly, it's going to be based off of your situation. Every situation is different. Every situation might call for specific requirements. By far, that is more important than anything else. Every situation will be different. So make sure your situation is met by whatever form of cabling that you're doing meets your situational needs. I apologize for that. Last slide that we got to talk about is our measuring transmission media capacity. So, what is our capacity? I specifically want to look at this slide. I don't really care about the noise slides. I mean, they're heavy mathematic based. Basically, the more noise you have, the smaller the capacity, which means you don't have as much capacity. That's essentially those few slides that we skipped over. That's what those state. So, the last slide is all about signal or channel capacity. The higher the frequency, the more data we can stick on it, which means the more data we can transfer. Higher frequency typically means faster connection. We're getting to the point where our wireless can be gigabit speed. Now that's theoretical right now. We're looking at 802.11 AC, AE, A something. Too many acronyms to remember. But it's the postcursor after N. And they are actually supposed to be pushing almost gigabit speed. But just like anything else, it gets affected by noise, it gets affected by the environment, and so it really all depends on your situation and how you're implementing it. That's really it for this chapter. If you have any questions, please let me know. If you have any comments on how I can make this better, again, please let me know. I hope you had a good time, and thank you. Have a good afternoon. Goodbye.